هنقدر نبدأ يا دكتور، اتفضل.
Okay, can I start?
Yes.
Okay. How many minutes do I have just for me to know?
The session is until 7 p.m. So we have 40 minutes.
40 minutes, okay. So I want to thank everyone for attending this presentation, and thank you for the organizers as well, and I hope it will be beneficial. So, and I hope also my voice is clear. So basically in this presentation, I will try to summarize the findings and results of a project, which we have just concluded, and we also obtained a US patent for the results that we got from this project. And the title of the project, as you can all see, is High-Speed Microplasma Through Random Bit Generator for Real-Time Encryption Applications. The members of the project were myself as a principal investigator and my co-investigators, Dr. Hussein Al-Awadi, Dr. Anis, both of them from the University of Sharjah, where I work at the moment. And also we had a postdoctoral fellow who was working with us on the project, Dr. Andrea Rocha, and the project was completely funded by the Dubai Security Authority. So as you all know, these are the team members that were doing this project. Again, myself, Dr. Hussein Al-Awadi, Dr. Anis, and our postdoc, Dr. Andrea. So as you all know, today there are so many challenges in security, and it is very important that we try to obtain security, whether on the software or on the hardware levels. Now, on the software level, there are a lot of work that has been already done, but in the hardware level, security is becoming more or less crucial for military applications, for banking and financial transactions, and all of these require more security than what can be offered by the software level security. So this is why there is a lot of work going on into the random number generators, which are basically the heart of any encryption system nowadays. If you want to be able to do secure communications or secure data transfers, you need a reliable and also, if possible, a high-speed random number generator. And there is a lot of work going on finding different sources of randomness, not only by using, digital hardware-based or computer-based solutions, but physical random sources or physical sources of randomness. So we can actually divide randomness or random number generators into two different types, physical and pseudo-random number generators. The pseudo-random number generators are the ones that we are more familiar with. They use algorithms and they run on hardware platforms, whether they are microprocessors, computers, microcontrollers, DSPs, and so on. And these pseudo-random number generators, as you can see from the name, they are not really random. They are actually pseudo-random. That means they can be, if someone targets to get the code or the randomness code, you will be able to do that because they are somehow repetitive. Now, in the physical domain or physical random number generators, these random number generators rely on really physical phenomena, such as, for example, radiation, or random behaviors in radiation, and other sources of noise sources, temperature fluctuations, other sources of randomness that are physically random. But of course, this type of physical random number generator is difficult and more expensive to realize because it cannot be integrated easily on chips. And that is why it is also more difficult to attack and more difficult to remove its randomness. Now, the famous solutions that are available in the market today, for example, the famous chip from Intel, which relies on jitter or jitter noise basically you have multiple ring oscillators producing different waveforms, and by sampling or high frequency sampling these different clocks, the jitter or the noise that is available in the waveforms is used to produce random numbers after, of course, some post-processing. So the most of the solutions today are based on this chip here from Intel. But there are other standalone solutions which are also relying on physical sources that I will show, or that I will show one of them now. So our solution in this project was basically to rely on a phenomena called plasma. And basically, plasma appears when you put an electrode in close proximity to another electrode, or the electrode in close proximity to a fluid, for example, liquid, such as acids, for example, and then you apply a high voltage. Once you apply a high voltage between two electrodes, or an electrode surface and a liquid surface, the plasma starts to show. And this plasma is just like lightning. When there is rain, for example, you hear thunder and you also see lightning. This lightning is actually plasma. So the plasma is arising from the breakdown of the insulation between one electrode and the other. And we studied this behavior, the behavior of plasma, and we found out that it is highly random, and it is more or less impossible for anyone to predict this type of waveform that arises from the breakdown of the insulation between the two electrodes once you apply high voltage between these two electrodes. So in this slide, I show here, for example, results of the plasma current waveform when you apply a voltage of 60 volts, which is considered to be, of course, high enough in this case. When you apply such a voltage, 60 volts, across two electrodes, one of them in the experiment that you are seeing here, one of them is metal electrode, platinum electrode, and the other one is the surface of a liquid, and the liquid in this case is an acid. So once you apply this high voltage, a breakdown happens in the insulation of the air between the electrode and the surface of the liquid, and as a result, a current waveform that you can see here measured in milliamperes is erratic behavior or random behavior, and the power distribution, as you can see in the subplot, is more or less a Gaussian distribution in terms of the distribution of the different amplitudes. So by using this type of waveform, which is highly random, we can produce random bits or a random number generator that is based on this physical phenomena, which is called plasma. In our preliminary results, I'm showing here some preliminary results. We could operate at different voltages from 40 volts up to 100 volts, and we can obtain bits up to 2 megabit per second. And of course, we might need some post-processing, but the post-processing of the data here is very simple. A simple XOR function, for example, is enough in order to produce random bits. These results were already published previously in two journals. One of them or both of them in the Journal of Applied Physics. And the first article is True Random Bit Generators based on current time series of contact glow discharge electrolysis. And then the second one was a little bit earlier, nonlinear time series analysis of current signals from the plasma discharge. So this type of plasma behavior, as you can see from the figure, produces a highly random current, not by applying a high voltage. And this is the problem of this device, which is basically you need to generate a high voltage starting from 40 volts all the way up to 100 volts in order to generate the plasma. But the advantage of this type of high voltage is that also it is impossible to attack this device. So as you know, today there are so many attacks that are being performed on different security systems. So for example, one of the most famous attacks is called frequency injection attack. The one that is shown in the figure here on top, on the top right of the slide. So what is this type of attack? Assume that I have a secure microcontroller, for example, and this microcontroller is running a random bit generator is already implemented inside this microcontroller for any type of security purposes. I can easily inject a signal from outside of the microcontroller by using a function generator and a simple RC circuit like this 50 ohm and 47 nanofarad coupling capacitor. I will inject this signal from a function generator in the lab to the power supply pin of the microcontroller. And by adjusting the frequency of this injected signal, it is possible, after, of course, trial and error and some long data gathering, but it is possible, and it has been shown by many people to be very simple procedure to do. It is possible to inject a signal that will actually stop the microcontroller from being secure anymore. So the random number generator inside the microcontroller can be stopped or can be attacked by this simple technique of injecting a frequency or injecting a signal with from a function generator outside of the chip. Now, this is possible, of course, because the signal that we are injecting here has low voltage, and it is injected on a power supply pin, 5 volt, for example, for a typical microcontroller. And this makes these types of attacks very simple to do or easy to do when you have a security system built on a DSP or built on a microcontroller or built on any system that requires a 5 volt power supply or a small DC power supply. If I go back to the previous slide, I can show you that our plasma system, for example, requires 40 volts all the way up to 100 volts in order to generate the random behavior or the random data from the plasma system. And this is what attracted us to do this type of solution. It is impossible to attack this source of randomness, and therefore it is impossible to break the randomness of this type of system, because any attacker would need a really high voltage, 40 to 100 volt, in order to attack the system, which is not easy to produce from a standard, for example, function generator in the lab. So this solution, by using plasma as a source of randomness, is not vulnerable to external injection or frequency injection attacks. Also, there is another type of common attack, which is basically electromagnetic wave attacks. You can attack a secure system by simply injecting it or by simply attacking it through an electromagnetic wave, not direct injection. And since most of these security systems rely on low voltage power supplies, it is easy to attack them. But once you have a random number generator that is based on high voltage, it is not easy to attack such a system. On the left-hand side, I show you some of the NIST results, the standard statistical results that are shown for this microplasma system. And you can see that all the randomness tests have been passed successfully with the applied 60 volt DC, as you can see on the left, and also after applying an attack. So on the second column in this table, if you look at the second column, we have a 60 volt DC plus 5 volt peak-to-peak attack, and still the system is not vulnerable. It passes successfully all the standard statistical tests for randomness. We were able, for at least at the time of preparing these slides, we were able to record 60 megabits of data points, and we applied on top of the DC the DC supply a 5 volt peak-to-peak attack, and still the system was very secure, and it was literally impossible to break down its security. So the solution or the final solution that we have proposed in this project, and we have been able, as I said, to obtain a patent for this device, is basically a microplasma system that is powered by a high voltage 40 volt or above, and a very small tiny box which includes the 2 electrodes. Once we apply this high voltage, a plasma arc ignites between the 2 electrodes, and then we have a current sensor in order to detect the random current. We can also use the light that is emitted from the experiment to produce random data if we want. So there are two possibilities. Either you harvest the current, you harvest the randomness in the current, or you harvest the randomness in the light, the emitted light. And as I will show in a few minutes, we can actually produce randomness simultaneously from the random current and from the optical light that is emitted from the plasma. So I can open the door now for some questions, but before I do that, I wanted to show you one of the publications that came out from this project, and also conduct some more explanation, which will become more clear also in the article. So this is a publication that we have just published related to this project, where we are able to produce random bit streams from a single source of entropy. In this case, it is the plasma source. And we are using, or we are able to use, both light and current as two different sources for randomness. So as you can see, this is the simple illustration of the experiment. We have a high voltage, we have a microplasma system that generates the plasma arc, and we are measuring the electrical current passing in the battery or in the high voltage source. And also we are measuring the optical light that is emitted from the plasma. Just as a reminder, again, the plasma, you can look at plasma simply as lightning. Lightning that you see in the sky when there is heavy rain, there is lightning. This lightning is plasma. So you can actually measure the current passing in the plasma, or you can measure the light that comes out of the plasma by using an optical probe, for example, and you can measure the current by using a current probe, as you can see here in the experiment. Now, both signals that are produced from this plasma system, the current and the light, both of them are random, are truly random. So there is no way that they repeat, and they follow a distribution that is typical of random signals, as I will show in the next figures. So just to show you typical waveform, the typical waveforms that appear from this system, you can see the green waveform is the electrical current, which is, as you can see, random, and it follows the random distribution. This is the power density function. You can see that it is follows the normal distribution of random signals. Also, the yellow or orange signal is the light that can be captured from this plasma. And again, it is a highly random signal, and it also follows the power distribution function. As you can see here is Gaussian power distribution function. So in these two signals, whether you measure the electrical current from the plasma or you measure the optical light emitted from the plasma, both of them are simultaneously random, but they are not correlated with each other. So that is why you can use them as two separate sources of randomness. As you can see over here, we can easily prove by so many different tests that these signals, current and optical, the current signal and the light signal emitted from the plasma, both of them are truly random, and they are not correlated to each other at all. If you are interested, of course, I can post these or post the links for these papers at the end of the presentation for anyone who is interested. These are the typical NIST tests, statistical tests performed here on a 20 megabit long data bit sampled at 500 megasamples per second. And you can see that for both the electrical current and from the light or the photo emission data, both of them successfully passed all the statistical tests, and the system is a dual random source by using both current and light emitted from the plasma system, as I mentioned at the beginning. So I think I go back to the slide and open up the floor for any questions. Anyone who would like to understand more about this plasma system, please go ahead and ask any question that you wish.
Thank you, Dr. Wakil, for this presentation. Actually, it's very nice presentation in a very hot topic part, and thank you for coming for our session. And actually, it's a pleasure to have you in our series here.
Thank you very much,
Hope
Dr.
that
Madden. I mentioned at the beginning that actually I completely forgot, or no one actually reminded me, but anyhow, I managed to, because
you always ready, Dr. Rocky. I know that you are always ready. Don't worry. I was asking about where do you see the future of such a kind of using plasma in such type of application? Because I know there's a lot of other parts that are already using the same generation for the bitstream.
Yeah, I would just like to show you actually the final. I think you can all see the screen, correct? You can all see my screen?
Yes.
Yes, so I can actually, to answer your question, I just wanted to show you the final prototype of this project, which we have actually assembled together in a factory here in Dubai. And this is basically the final product of our project, which was patented, and we are looking or trying at the moment to find someone who is interested in commercializing this project and moving forward to the industry. Just a brief explanation of this random number generator box. You can see there is a simple typical battery. It's a battery that can be rechargeable, and there is an electromagnetic probe here, or current probe if you wish. The arrow points to the current probe. We are harvesting the random current. There are two electrodes. Between these two electrodes, once the system is switched on, between these two electrodes, the plasma appears. And once the plasma appears, this means the random behavior or the random current starts to show up. We measure this current by this electromagnetic probe, the black stripe electromagnetic probe. And then the data is connected to a standard data acquisition board. In this project, we just used the Digilant data acquisition board from Analog Devices. It's a very easy to use data acquisition board with a very small size and easy to program. And we use this data acquisition board just only to sample the current data, which is random, and then communicate directly through the USB with the computer in order to transfer the random data, some of which is stored here in the data acquisition and directly later on transferred through the USB to the laptop or computer or whatever. We also developed a software that runs with this system. So it's a very simple system to use. Plug it in your USB, start the plasma, and you can harvest randomness. So to answer your question, we are in a phase where we have basically patented the solution. We obtained the US patent, and we designed a prototype which is ready for commercialization. We are just now negotiating with some partners here, trying to move to the next step, which is basically commercializing this product and selling it, or at least it will be used in Dubai here by the Dubai Electronic Security Authority, which is the funding agent of this project. Dr. Madian, can you hear me?
Okay, but does it affect? Do you hear me?
Yes, I can hear you. Go ahead, please.
Yes. Does it make any effect on the lifetime of the battery or something like that? Does it shorten that or not? Did you start this?
Yes. You are asking a very important question. Of course, we have a lot of results but the time is not enough to show. So we also studied the effect of the life of the battery on the randomness. So as you just mentioned here, it is expected once the battery starts to drain, the amount of charge in the battery goes down, the randomness starts to become degraded. And we were able basically to characterize the system and obtain the specific requirements from the battery. So with the type of battery that is installed at the moment, we can keep this system running for about, we can gather from this system about 10 gigabits without any problem at all. After this, you need to recharge the battery and in order for the randomness not to degrade. Also, we installed in the software that we built a feature that basically can detect when the data is no longer random enough, and it will notify the user. So he has to stop collecting data and he has to recharge the battery in this case.
Does it have an if we have does it work with a hybrid solution like working with solar cells or something like that, or we didn't try to find something like that?
No, really, we didn't. We were focused here on just working with battery. And as I said, also, you can see we are not even relying on the USB voltage from the computer. We are relying on a separate battery here to avoid any possibility of attacking the system, because also this the current that is produced in the plasma is high. It can reach up to 3 amperes.
I see.
So it's a high current and it's a high voltage. Under this board, there is another board that you cannot see. It's a high voltage DC-DC converter, which takes the battery voltage and produces a high voltage. As I said at the beginning, we need something between 40 to 100 volts. So there is another circuit underneath this data acquisition board. There is another converter that produces the high voltage, which is enough to create the plasma in this case.
I see. Actually, it's a very good solution, but that's why I'm trying to find the different options around that. But is it costly? Did you study the cost for something like that?
Yeah, you will be amazed from the cost. The cost is actually only the data acquisition board. The remaining stuff, the battery and the parts of the electromagnetic probe. Of course, the quality of the electromagnetic probe is very important. So we did a lot of research until we chose the best type of electromagnetic probe. The black one here is the smallest size and the highest possible quality. But in all cases, the highest cost is actually the data acquisition board. The plasma system itself is not that expensive. The data acquisition board is quite expensive, about $200. The rest of the system altogether, the electromagnetic probe, battery, DC-DC power supply, and plasma electrodes, this is not more than $100. The whole system altogether is about $400, which is much cheaper than other solutions in the market.
Yeah, it's really, it has already a good cost relative to the function, yeah.
Yes, there are other solutions in the market that rely on lasers, randomness from lasers and optical sources. They are very expensive. This is the only product or the only project that relies on plasma. So we are not aware of anyone else that has tried to use plasma before, and that is basically why we were able to patent this device. If there is time, I'm not sure if you have time, but I have a video.
Yes, we have time. Yes.
So I can run a video, short video, just to show you one of. Oh, this is not the one. I think I have another video where I basically just demonstrate one of the prototypes that we had before.
Sure.
If you have time, I can show you this. It's not. I don't know why it is. This is the old one. Okay, so let me see if I can run this. Okay, can you all see the video here?
No, I can't. I think you have to share the video.
I'm sharing my screen, so you should.
I don't know, but I see the board only.
Oh, you see the board only? Okay. So in this case, let me. You can still only see the board, yeah?
Yes, the board only.
This is where we're gonna.
Now it's moving the board. I don't know.
Yeah, can you see the video now?
No, actually, it's still the board, but the board is not exactly. I don't know if this is me only or.
What you had before, but I installed the newest version of the application.
I have the same problem.
So this is
Yes, the video now is okay. The video now is working.
Can you see the video now?
Yes, yes,
Okay, so
yes.
I will restart the video. Okay, and basically this is just showing you the whole system, the box that we developed connected to via USB to the laptop, the software that we developed for the Dubai Security Agency, and everything running all together. And if you pay attention, once the video runs, you will be able to see the plasma, the light appearing. So I will start the video now.
we are trying I installed the new version of the newest version. I'm not sure what you had before, but I installed the newest version.
You can all see the plasma light.
Application.
Yeah, I think yes.
I will, yeah, this is the plasma light. You can see that. I will stop the video. You can see at the very bottom, the plasma light. So this is the plasma light that we are harvesting, and once you switch on, your plasma appears, you collect the data, and the data is transferred to the computer. Then you switch the plasma on again. Is it clear, the plasma?
Yes.
Dr. Madian, is it clear?
Box and the laptop are ready for.
I think yes, I see that. Yes.
Yes. Okay. So this shows you how the box works. You ignite the plasma for a few seconds, collect about 1 gigabits of data, transfer it to the laptop through the software, and then the software will do the statistical randomness tests. Any data that is not random will be removed or discarded. If the data is random, it will be kept or saved in a file on the laptop. You can see here it has already started to do the test. So we finished collecting the data, and now it will start doing the randomness or the statistical test. The software that we developed is actually quite sophisticated. It's a complicated software, and we used it for a very, very long time. We tried the system for about 3 months, continuously running and collecting data just to make sure that we don't have any trouble, there is no problem, and it's reliable, and it is actually very, very reliable. I can try to skip this a little bit. I don't think the results will show up. So this is basically one of the many videos that I have here, and we developed also several prototypes. I can show you an older prototype if there is some data, some time. Otherwise, you can stop me. This is another prototype, same thing, but different case. Now, I think you can all see the plasma clearly.
But do you have a special condition for such a kind of experiment to avoid noise effect and the other sources around?
We don't have, there doesn't require any ethical permission, any specific permission, but only when we build the final prototype, we had to do some safety tests just to avoid anyone getting shocked by the high voltage, because I personally got shocked several times by the high voltage. God. Yes, I got shocked several times when we were building the device due to the high voltage. And we had to do some tests. So this initial prototype, the one that you are seeing here on the screen, this is not the one that was finally produced. You can see this one is dangerous because the plasma electrodes are outside of the box. But the final prototype, we had the plasma electrodes inside the box, and the box was sealed, completely sealed. You cannot open it. You cannot, there is no way that you can touch this high voltage or get shocked from the high voltage in this case.
I see. But there's no effect of noise or something like that, right?
No, there is no effect of noise. There is only some smell ozone, once the plasma is ignited, you actually can smell ozone.
I see. Okay, but I think it will not be that harm, يعني. صح?
It's not harmful. It's not that harmful, يعني, but it is a very distinctive smell. You can always smell the ozone being produced from the oxygen in the air.
I see.
On the screen here, you can see that just the system, the software that we developed, and it is collecting the data. After collecting the data, it binarizes it, and then it passes it through the standard statistical tests. And then you can repeat collecting the data again and again. So I'm just trying to skip. I don't know. This was quite an old prototype, but it just shows you the working principle of the system. So we are in an advanced basically state where we have a complete prototype tested. We have a software running. We are just looking for the right place to commercialize our product. On the screen here, you can see NIST testing. The statistical tests are embedded in the randomness tests, NIST tests, if you are aware of these. They are embedded in our software. So basically, once the data is collected, it will automatically start doing the randomness tests, and it will show the user whether his data that has been collected is truly random or not. If it passes all the tests, it is random. If it doesn't, then he has to repeat, or he can ignore the data that has been collected and repeat again, collecting the data one more time. But as I said, we tested this system for over 3 months and continuously running, and we really didn't have any issue from the randomness. It was always passing all the tests.
Just one question that raised in my mind now, Bastin, does the temperature has an effect on that?
Well, the temperature, you mean the outside temperature or the temperature of the electrodes?
I think the temperature of electrodes, because working for 3 months is, I think the electrodes temperature will be maybe change a bit, right? Or
well, we actually performed the tests only inside the normal room temperature, but there is an important issue related to the temperature of the electrodes, which is basically what happens when this plasma arc appears. So I will go back to the beginning of the video. When this, you can see here on the screen, you can all see the plasma, correct?
Yes, I can see that.
The arc or the plasma being generated. This plasma is not only high voltage, it is also high temperature. So
I see.
What happens is that that is why you can smell the ozone. The ozone is produced because of the high temperature between these two electrodes. But because we don't switch the system on for a very long time, the system is switched on for a sufficiently short time, then as you can see here, we stopped the plasma. We got enough data. So we don't really switch it on for a very, very long time. So therefore, the heating effect of this plasma is not that much of a problem. It will be a problem if you keep this arc or this lightning arc on for a very long time. In this case, you will really have a problem.
I see. Yeah.
So any more questions, Dr. Ahmed, or any of your audience, please go ahead.
Doctor,
so yes, go on.
I want to know the name of paper if available. Yeah.
Oh, the publication?
Ayo.
Oh, yeah. Yes. I can go back to the. Okay, can you see the screen?
Yes.
The paper title is there. Can you see it?
No.
Hmm?
No, not clear.
I shared it, but it seems that there is a problem with the sharing. So let me share again. I don't know why it is not sharing. You cannot see my screen at all?
No.
Okay. Okay, I will close all tabs and I will reshare again the. So what can you see now in front of you?
Nothing.
Please.
Oh,
Nothing.
nothing. That's very strange. Okay, let me try to share again the screen. Maybe there is a problem with the internet. I will try to see again where the paper is. Okay, I will send it to Dr. Ahmed after the presentation. I will.
Okay, no problem. I can share it with the RAs and the other attendee.
Yes, I will send it to you by email, and it is easy to. Okay, let me try one last time. Okay, if possible, to share the screen and see what is the problem. Can you see it?
Yes, the screen now is okay. Yeah, the screen now is okay.
Okay, so this is the latest paper. We have published 4 papers and 1 patent. The latest one is this one, published in the journal called Plasma Processes and Polymers. The name of the journal is in red on the top right on your screen. On the top right, the journal's name, Plasma Processes and Polymers. This is a journal by Wiley, published by Wiley, and the title of the paper is here: Parallel Random Bit Streams from a single source of entropy based on non-thermal electrochemical plasma. Is it clear?
Yes, okay. Thank you very much.
I will anyhow send to Dr. Madian all the 4 publications that came out from this project, and you are always welcome to ask any questions.
Dr. Ahmed, may I say something? I don't have questions, but I would like to express my feelings about the presentation. It was wonderful, and the talk was very informative as usual. Thank you so much for giving us new insights about new topic as always. Thank you.
Thank you very much, Lubna. Anyone interested to continue to work on this direction, there is a lot of work still to be done in hardware random bit generators using plasma and using other sources. We are trying also to combine now some other sources together with the plasma, and to study more the effects of temperature, the effect of humidity, the effects, all different other effects on the quality of the random bits being generated from this system. So any more questions? Can you all hear me?
Yes. Yes.
Is there any more questions?
Any question from anybody? So I think we have reached the end of our session today. Thank you, Professor Elwakil, for coming today, and actually we are very glad for giving us this session in such a very interesting topic. Actually, I think this topic is need a lot of research, I think, and there's a lot of points that you already have opened today that already need to be covered. So thank you for your presentation, and wish to meet you soon in Egypt, inshallah, when you come in a visit, inshallah.
Thank you very much, Dr. Madian, Dr. Lubna, and all the rest of the attendants. Thank you very much for your time, and please feel free to contact me anytime if you are interested in any further details about this project or any further information related to the prototype that we have developed. Thank you all very much.
Thank you, Professor Elwakil. Thank you so much. Thank you.
Thank you. You're all welcome.
Thank you all for coming today, and thank you for attending our session. And see you next week, inshallah. Assalamu alaikum.